Hi, welcome to the next session. In the last session, we just had a look on the basic understanding of what PyTorch is or why PyTorch is getting popular over a period of time. Now, to start further, there are certain things, certain terminologies that you need to know. Like, for example, the very first terminology that you need to know is the logic of computational graphs. Now, PyTorch is a brilliant or excellent platform which offers dynamic computational graphs. That means it basically converts stages into the form of graphs or into the form of sort of flowcharts. Okay, so it offers you dynamic computational graphs. So, with the help of PyTorch library, a user can change them during runtime. Means while the code is running, you can change these graphs at any point of time. That is why they are known as dynamic computational graphs. So now this particular feature of that a user can change them during runtime as well. So it is highly useful, particularly when a particular developer or has no idea how much memory is required for creating a neural network model. Now, neural network model ideally requires a lot of memory, though it is totally dependent upon the size of the model that you are expecting to draw on. But since normally at earlier stages or initial stages, it's very difficult to make any prediction with respect to the size of the model and or the requirement of the memory according to the size of the model. So a user need to change them at any point of time while the code is already running. So that is where PyTorch acts beautifully because it offers you the formation of computational graphs in a dynamic way. So there are three important terminologies that you need to understand when we talk about PyTorch. The first and very popular word is the word tensor. Okay. So all of you must have heard about the Tensor library. So Tensor is simply a n-dimensional array. Okay, it's nothing. It's an n-dimensional array which runs on GPU as well. Okay. Then another word is variable. Now variable is basically a node in a computational graph. Okay, so since a computational graph consists of nodes, so the node in a graph is known as a variable. So the ideal objective of a variable is that it stores data and the value of gradients. Okay, so gradients are there when we go with backward propagation. So we'll understand about it in detail later on, what all this is all about. But variable is simply a node in a computational graph, and the ideal objective is that it stores the required data and the gradient values. The third important terminology that we should know is the module. Okay, now this is that layer of your network which will store the state or the learnable weights. Okay, so when we talk about a neural networking model, the concept of weight is very important. Again, we would be dealing with this thing later on in detail, in very much detail actually, that what is the concept of weight while we are drawing neural networks. So for storing these learnable weights, the modules are used. Okay, so tensor, variable, and module. These are the three very specific terms. Tensor is simply an n-dimensional array which can run on GPU as well. Variable is ideally considered to be a node in a computational graph whose job is to store data and the gradient values. And module is a that layer of a neural network which store the learnable weights or the weights learned during the process of neural networking. So tensors, as I said, they are just similar to if you compare in terms of NumPy. Okay, so tensors are similar to NumPy arrays uh, with an addition that they you can also use them on a GPU to accelerate the computing. So in case of complex and complicated tasks, GPUs are required, or high speed tasks GPUs are required, and So to work with GPUs, NumPy is not possible. NumPy cannot work with GPUs. So therefore, tensors are used, and that is where they provide a additional benefit. Okay, so you can use tensors on a GPU as well. Ideally, we can say tensors are just similar to NumPy arrays, the way we define NumPy. Okay, so NumPy is one of the very strongest libraries when it comes to numerical computing in Python. Why PyTorch? So if we try to gather a few important points here. One, it offers a strong GPU support because it's very important in case of complicated and complex tasks. GPUs are definitely required. So strong GPU support is a very additional advantage which the PyTorch offers. Then many algorithms which are of great use to us when we are doing neural networking or deep learning are already implemented, so you don't need to implement them separately. Then it allows automatically differentiation. Differentiation is again very important part of neural networking, and it's similar to NumPy. Okay, so when we talk about neural networking, when we talk about deep learning, we talk about computer vision, image processing, and so on. Uh, the data is ideally present in the form of arrays. Okay, in the form of integers, in the form of numbers. So uh, NumPy, since NumPy is not viable to run on GPUs, or it cannot be used for that level of complex or complicated processing, so therefore PyTorch tensors uh, act as a great replacement to that. Okay, so that's where the use of PyTorch is there, and that's how it offers great flexibility, speed, and super processing power to enhance your deep learning or neural networking. Now, we only need two imports at this stage. One, I would like to import the print function, okay, because that is not inbuilt with the torch. So from future, I will import the print function. And the second important import that I need is to import the torch, okay. So like we import NumPy as MP, okay. For example, if you want to work with NumPy, so you have to import NumPy as NP. NP is a abbreviation or a context for running NumPy library. Okay, so you don't need to tie NumPy again and again. NP is good enough. In the similar way, when you are working with PyTorch, you need to import torch. Okay, so torch acts as a context for PyTorch, as simple as it is. Now, since we'll be working with matrices, because when we talk about computer vision, image processing, and all this stuff, the data is ideally reflected or designed in the form of matrix only. Matrix is basically simply acts like a table with columns and rows. So the data is majorly available in that format only. So that's why we are talking about matrices. So when we talk about an uninitialized matrix, uninitialized matrix means it does not control any definite known values. So whenever you are declaring an uninitialized matrix, that means you are not telling or you are not putting any known or definite values to it. You are not giving any definite values to it. So in that case, whatever values were already there in the allocated memory will appear as the initial values. Okay, so either you define the values which a matrix needs to take. If you will not define, then in that case, whatever values are present in the allocated memory at that particular time will be shown as an output, simple, or will be shown as the initial values. So that is what the uninitialized matrix means. Matrix simply means you want to reflect data in the form of table with rows and columns. And since when we talk about deep learning or when we want to apply the neural networking, the majority data or 99% or greater than 99% of the data is present in the form of this format only. So when we talk about an image, okay, you want to process the image or you want to do some processing on image, then ideally the image data is has to be represented in the form of matrix only. Okay, so the concept of matrix is very important. That is why the concept of numbers is or arrays is very important when we talk about deep learning or the uh, application of deep learning with the help of PyTorch library. Okay, so in the next session, we would be having a small comparison, or we'll take few examples to compare PyTorch with NumPy. Now, since we say that the PyTorch is an extensive advancement of NumPy when it comes to applying deep learning or neural networking or performing complex or complicated tasks. So once you will understand the difference, or once you will be able to compare the functioning of NumPy and PyTorch, you will realize that it's almost similar. So whatever commands we used to run on NumPy, the similar sort of commands will run in PyTorch as well. Just a little bit change is required in the form of context calling. Like for example, when you are applying NumPy library, you use NP as a context. So definitely in Torch, the same thing will not happen. But the overall conceptualization of writing the code will be almost same. Okay, that you will see when we'll go into that. Okay, so in the next session we'll start off with the comparison of the PyTorch with the NumPy. Okay, or the matrix formation using PyTorch and the matrix formation using NumPy. So you'll automatically realize that what are the similarities and where the difference exists. So till that time, keep practicing, and thank you so much. Hi. So as described in the last session, this session we would be concentrating on we'll be starting off with the comparison of PyTorch with NumPy, and come to know that when you will be running these basic operations, that more or less both gives you the same output, or the commands, even the input commands are also uh, or doesn't have much difference. Let's start with the matrix formation using PyTorch. So the very first thing what you need is to need the import the torch module, okay, because that's what we are working with. And finally, you want to create a tensor, okay? So in PyTorch, as I described you above, the tensors are the n-dimensional arrays, okay? So let's go above and let me show you again. So tensor is an n-dimensional array. The ideal difference that it can run on GPU, which is difference, the basic ideal difference between tensor and NumPy. So to make an array, you need to call dot tensor. So normally when we are using NumPy, we don't use the word tensor, we use the word array. Okay, but here we will use the word tensor. So I want to create a tensor or an array. So I will call torch the dot tensor, and then I prescribe you the values like I want 2, 3, and 5, and 1, 2, and 9. So let's run it and let's see how the code works. So as you can see that it has created this array with me. The first row consists of values 2, 3, 5, and the second row consists of values 1 to 9. Okay, so matrix, as I told you, it's just like uh, an array, or shown in the form of tables. And since majority data is available in tabular format, so matrix are the most used concept when it comes to deep learning or neural networking. So this is the first row that you want to put containing elements 2, 3, 5. This is the second row you want to put containing the elements 2, 3, 5. Okay, and when you call it, so you see the array has been built consisting the values that you have defined above. So that's simply how you can form a matrix with the help of torch. If you don't want to put up any specific values, just want to draw a 2 by 2 matrix randomly, so you can say torch.rand. That means you want to draw a matrix on the basis of random, a 2 by 2 matrix on the basis of random numbers. And if you run this code, This play button will run the code for you. So you say 2 by 2 matrix is there. Now since it's an uninitialized matrix, okay, and you are giving random, so the system will select, or the application will select any four random values. So 2 by 2 matrix, two rows, two columns, as you can see in front of you, have been put up as an output. Then then it is a. Now suppose I just want, I'm basically creating a variable. So as I told you above, that variable is something which stores the value. So I'm creating a variable a, and I want to store a matrix, a 3 by 5 matrix, a 3 by 5 matrix with random values. Okay, so you can see now I'm defining torch.rand again, and this time I want to draw a 3 by 5 matrix. So let's see. So you can see now, since I have called a dot shape, that means I only want to check the shape. I don't want to print the matrix. So it is telling me that a matrix has been created with the uh, 3 by 5. That means 3 rows and 5 columns. So let's say if we print this matrix, let's say I say print A. Now you can see a 3 by 5 matrix has been built in front of you, consisting 3 rows. Okay, this is row 1, this is row 2, and similarly row 3, and similarly there are 5 columns. So the first argument will tell you about the number of rows that you want to keep in the matrix, and the second will tell you the number of columns that you need in the matrix. And now since I'm putting random values, so random values have been selected by the random function. Okay, so this is how you can form a matrix using PyTorch. So either you can put up your own specific values, that is option 1, or second option is that you can uh, do it on random basis. You can just tell the system what level of matrix you want to build, and the system will choose the values accordingly. Then let's see how to form a matrix using NumPy. Now I have taken the same examples which I have taken above, but this time I am not applying the matrix formation with the help of PyTorch. I want to apply the matrix formation using the NumPy module. So we'll import the NumPy as the NP. Okay, that's the basic import that you need to perform if you want to use NumPy library. NP, as I told you, is the context for using NumPy, so that you don't have to type NumPy again and again. You can type the small form NP and the work is done. So I will say np.array. Earlier, when we were using PyTorch library, it was torch.tensor. Okay, so torch, the module that you are working with, and instead of array word, we have used tensor earlier. So now np.array, and you can mention the prescribed values of your matrix. So you run this, and the matrix or the array of prescribed values is there in front of you. Similarly, if you want to work with random numbers, so it was torch.rand earlier. It would be mp.random.rand. Okay, in NumPy, just a little difference of the commands. np.random.rand. You want to initialize it 2 by 2 matrix, and you click just run, and you see a 2 by 2 NumPy matrix or array is there with you. Similarly, again same example. I want to draw a random matrix. Okay, with 3 by 5 size 3 by 5. Okay, and let's say let me print this matrix for you so that it's more clear. See, so 3 by 5 matrix is right there. So with consisting 5 rows, or sorry, 5 columns and 3 rows. Now since you have done on random basis, it is giving you random results. Okay, the output will not be same because in random cases the random figures are taken, so output can never be same. Okay, but when you have defined specific values, you can say it will show you the output in exact way. Now this was the output when we have built an array using torch, and this is the output when we have built an array using the NumPy module. Okay, it's absolutely and exactly same. Then if you want to construct a randomly initialized matrix, okay, so which I have described above also, that I want to draw a random matrix using torch module. So we can take torch dot rand. Okay, I want to declare a 2 by 2 matrix. Similarly, let's say I have defined another matrix B here. Again, 2 by 2 matrix on random basis. So now we have two matrices, matrix A and matrix B, two variables, variable A and variable B. And in both cases, I want a 2 by 2 matrix. So if you print this again, there is no point of printing here, because every time you will click on the run, it might select different values because you are using a random function. Okay, random function means it will give you random values. So let's run this. So now my variables have been decided, random values have been taken in the background. If you want to print, you can use print A and print B and see what are those random values. Now, we have run some other operations as well. Suppose I want to multiply these two matrices. Matrix multiplication is a very, very common concept. So we can say torch dot matmul, okay, matrix multiplication basically, matmul, and within the open and closing parenthesis, you can define the two variables you have, A and B, okay, and let's multiply them. Now, randomly, the matrices which were in the background have been multiplied. Then similarly, you can simply do this way also. You can simply write A into B. Now you can see the answer is not same because it might have picked different random values in the background. So either you can use torch.matmul or you can use A into B. So this is how you can randomly initialize the matrix and do any type of operation like we have done multiply operation here. Similarly, if you want to take similar example and create the randomly initialized matrix using NumPy, it's absolutely same. Only a little bit difference will exist. Like for example, again I have defined two arrays here, A and B. In both cases, I want to draw a random array of 2 by 2. Okay, so let's create and let's run this command. So in the background now, a 2 by 2 random array has been built. Now I'm using np dot dot. Okay, and np dot multiply. Now these are two commands we have used. Both will multiply the matrix, but in a different way. Okay, that's the difference. Let's say for example, let me print uh, A and B for you. Let me do it separately so it's more clear. Let's print A and let me go for print B. Okay, so this is A matrix, okay, and this is B matrix. Clear? So now I can perform multiplication in two ways. Either I can multiply this matrix normally, or I can have element wise multiplication. There are two different commands that can be run. Okay, and based on this, I will explain you the difference between these two as well, because this is where we have used matmul, okay, and this is where I have done the using the multiply method. Now, when we talk about np dot dot, okay, so it will give you normal matrix application, like first row of the A matrix multiply by the first column of the B matrix, and the sum would be there in the will be the output as the first element. But when we use dot multiply command, it will carry out an element wise multiplication. Element wise means the first element of A matrix will be multiplied with the first element of B matrix, and the resultant would be the first element of the output. For example, if I run np dot dot and if I run np dot multiply, two different operations. Okay. Now here, okay, let me open a calculator for you. Okay, so first element of A matrix was 0.57543845. Okay, that was the first element of A matrix. Multiply by first element of B matrix. So 0.497444879. Now you can see the answer is 0.2862511 and so on. This is shown as an output here when you have used dot multiply function. So using dot multiply, it will give you an element wise multiplication. So that means first element of A matrix will be multiplied by the first element of B matrix, and the resultant will be shown as the first element of the output. Similarly, the second element of A matrix will be multiplied by the second element of B matrix, and the resultant would be shown as the output. That is where NP dot multiply works, element wise multiplication. But NP dot dot is simply a matrix multiplication. That means first row of A matrix will be multiplied by second row of B matrix, and the sum would be treated as the resultant and shown as the output of the matrix. That's the difference between NP using dot command and dot multiply. Similarly, if you go above, let's understand this now. Okay, and let me uh, print both the matrices here as well. Print, sorry, A, and let's say print B. Okay, so two matrices have been created. I'm running the matpul and the multiplier commands again because since these are random numbers, the figures will keep on changing every time you will run. Okay, now let's use the calculator again. Let's see how this works. So let me first do element wise multiplication. So first element of A, 0.5619, multiply by first element of B, which is 0.3367. Now you see the resultant is 0.1891. If you see, this is shown here when you are using star command. So star command just functions like np dot multiply only. The way np dot multiply was giving us the result in the form of element wise multiplication. Similarly, when you want to do it using torch, then you have to simply use star command. But again, you want to do normal matrix application multiplication, then you have to use matmul. Let me see if it's possible to show by calculator. The first row of A, 0.5619, so 0.5619, the first element in uh, the first row, multiply by 0.2403, which is the first element of the first column of the B matrix. Sorry, no, this is not the value. This is 0.3367, so 0.3367. So I have multiplied the first element in matrix A, first element in first row of matrix A, multiply by first element of first column of matrix P. Okay, plus. Then we have second value in the first row of matrix A, which is 0.2519, multiply by, sorry to not carry the operation like this. It's not doing in a BODMAS way. So let me try it again. So 0.5619, okay, multiply by 0.3367. So the value is 0.1892. Okay, so that's the value by multiplying the first element of first row of A matrix with the first element of first column of B matrix. Okay, now the second is 0.2519, which is the second element in the first row of A matrix, multiply by 0.2030, which is the second element in the first column of B matrix. So this comes 0.0511 plus 0.1892, which the value we had already calculated earlier. You can see it is 0.2403, which has been shown here. So this is the result after normal matrix application. In the normal matrix application, the first row would be multiplied with the first column of the second matrix, and the sum would be treated as the resultant. Okay, so in case of torch, you have to use the matmul or the star command to do these calculations. In case of numpy, dot np dot or mp dot multiply. These are the two things that can be done for normal matrix multiplication or element wise multiplication. Okay, so this is how we can uh, understand the difference between using numpy or how to perform the same type of thing using numpy and the same type of thing using pytorch. Little bit difference in the input commands, but the way of processing in the background is happening in the same manner. Okay, so in the next session we will learn how to build some other types of matrices, uh, again by comparing the commands in numpy and in the torch. Okay, so till that time, keep practicing and keep focus or remain focused. Thank you so much. Hello, ladies and gentlemen. Welcome to the next session. And as discussed above, we talked about certain comparisons between the NumPy and the torch. So let us take few more examples so that we are more clear how the torch is applied. Let's say I want to construct a 5 by 3 matrix now, and uninitialized, I told you that uh, whatever values would be there in the memory at that point of time would be shown as the output. Now I want to create an empty matrix of 5 by 3, so I can say torch dot empty. Okay, and let's run this. So you can see whatever values were in the background have been shown as the output. Now it's a 5 by 3. That means there are 5 rows and 3 columns have been there. Okay, uninitialized, I told you, uninitialized matrix means a matrix where the values, whatever values are existing in the system in the memory at that point of time, will be shown as the output. Okay, so that is creating an empty matrix or an uninitialized matrix. So here we have taken example of pi by 3. I want to construct a matrix filled with zeros. Okay, so I can say torch dot zeros. Okay, a 2 by 2 matrix I want to create with zeros only. Okay, so let's run this. Let's run this cell. And okay, I need to print also because we have created a variable. So print a underscore torch. Okay, you can see a 0 by 0 2 by 2 matrix with 0 values has been created. Now if you want to create a 0 matrix using np command, that means the numpy, instead of torch dot zeros you have to use np dot zeros. Okay, so let's print this for clarity and print a underscore numpy. Let's run this. So you can see, so this was the torch dot zeros will give you a 2 by 2 matrix using 0 matrix using torch, and the same 0 matrix if you need using numpy you have to type np dot zeros. Okay, output is same, only the little bit command difference exists. Let's say I want to create a torch 0, again 5 by 3 matrix I want to create, and I'm given additional argument here which is data type torch dot long. Now, dot long means it would give you a 64-bit integer. Okay, that's what long format is all about. And let's print this. So 5 by 3 of matrix. Okay, so this data type will only convert it into that form to be used for complex calculations. Otherwise, you will not show any. You will not see any effect here in the output. Similarly, if you want to create a matrix of ones, okay, so instead of zeros, you have to type torch dot ones. So for zero matrix, you have to type torch dot zeros. That means a matrix with zero values. If you want a matrix with value one, so you have to type torch dot ones. So let's print this. Print, sorry, b underscore torch. Okay, and let's run this. Now see, all the values are 1. Okay. Similarly, if you want to use the same command using NumPy, so instead of torch.ones, you have to use np.ones. So print np, sorry, b underscore NumPy. Let's run this. So again, a matrix of ones has been created, but this time we have used the NumPy module instead of your torch. As example, let's say use np.identity. Now, what is the function of this dot identity? Now, again, it's an inbuilt NumPy function that will give you a 2D matrix or a 2D array having 1 at the main diagonal and 0 elsewhere. So the main diagonal of the array or the matrix will consist of 1 values and the remaining will consist of 0. So I will use mp.identity. I want to create a 2 matrix. Let's print this. Print c underscore numpy. Now you can see the main diagonal is having 1 values and there are zeros elsewhere. Okay, so you don't need to specifically mention here 2 by 2 because since only we are telling that's an identity matrix, you just writing 1 value is more than enough. So I'm writing 2, the function will automatically understand that you need a 2 by 2 matrix. If you want to run the same command using torch, so the command is torch.i. Okay, so torch.i will do the exact same work like print c underscore torch. So as you can see, the main diagonal consists of 1 values and the remaining are zeros. So if you want to do the same command using torch, no issues, using torch.i will work. Okay. uh, and the important thing that you should know is the conversion. Okay, so if you wish to convert a NumPy array into torch tensor and vice versa, that is very easy. Okay, now let's say for example, some we have already created above. Now I want to convert this c underscore NumPy, this particular array that we have created, identity matrix. I want to convert it into the form of torch. Okay, from NumPy I want to go to the torch. So the command goes torch dot from NumPy because I want to convert from NumPy to torch. So from underscore NumPy, that's the function we need to run. Okay, and I want to convert this particular array c underscore NumPy that we have created here. So let's let's run this here. Okay, so the command is run and let's print this. Print, let's see if d underscore torch. Now since if our command has been successful, then d underscore torch print function should return us the output, else not. So it is giving us the output. So that simply means that we have been successful in converging from NumPy uh, to tensor to torch. Sorry. Okay, this is how we can convert very easily. If you want to convert from torch to NumPy, okay, so like for example this c underscore torch that we have created above. Now it was a torch array, okay, or tensor array. So I want to convert it into NumPy. So I can use c underscore torch. This is the matrix or the array I want to convert, and I want to convert it into NumPy. So dot n NumPy followed by opening and closing parentheses. Okay, so let's print this because printing will let us know whether the command has been successful or not. Yes, the command has been successful and we have converting our torch or tensor array into a NumPy array. So conversions are very easy. Just simple one line command would convert your entire array into torch and vice versa. Then next is creating a tensor directly from the data. Again, we have done this example above also, where we have specifically mentioned the values. So torch.tensor. So if you mention the values in your print, it will simply give you the required values that you want. Okay. If you wish to change the data type, that can definitely be done. Okay, let's say for example, I want to create this particular tensor. So I want to create a tensor based on existing tensor. That is also viable. So these methods will reuse the properties of the input tensor. So whatever properties or features were attached to the input tensor, the same properties would be attached to the new tensor as well. So again, now the next we'll go is how to create a tensor based on existing tensor. Okay. So in the next session, we'll look to that. Till that time, keep practicing. It's very important to practice. Uh, I have again said it repeated number of times, and I say to my learners always that certificates are only the recognition that you have done something, but the prime importance lies in learning, because when you actually work in the corporate world, it's the learning that matters. Like once you sit on the interview table, then you start applying things. It's all the application stuff that goes. So unless until you are able to apply, certificates won't help you. Okay, that's why again I can say that practicing is very important, because that gives you that touch, that gives you uh, that strength and that confidence to work with the data. Okay, so till next session, thank you so much, and we'll meet soon. Hi. So I hope everything is going good and you people have been practicing meanwhile side by side. I don't really believe on the concept of practicing at the last. Side by side is, simultaneous practicing is the best. All right, so we were on creating in tensor based on existing tensor. That's what we need to talk about. So as I told you that if you use an existing tensor to create a new tensor, it will reuse the properties of the input tensor. Like for example, whatever data type was defined with the input tensor, the output tensor would be of the same data type. Okay, unless and until new values are specified. So now I want to create a new tensor x based on the old tensor x. This is the old tensor which is already defined. X we have already defined here. Okay, so I want to create a new. So I will say new underscore. Okay, so new underscore method will take in the size. So I say new underscore ones. So I want to create a matrix of ones. So I have used ones. Okay, and I want to create a 5 by 3 matrix, and data type is torch dot double. Now torch dot double will return you 32-bit floating point number. The difference between torch dot double and torch dot float argument is that using torch dot double data type, you can go for this 32-bit floating point. It will give you as an output. If you're using torch dot float, it will give you 64-bit. Sorry, I'm really sorry. Torch dot double will give you 64-bit, and torch dot float will give you 32-bit floating point number. The ideal difference of using 64-bit and 32-bit floating point is the bits. Okay, the data which is taken in the form bit. 64-bit, if you're using 64-bit floating point, then uh, the number of bits it can take is more as compared to 32-bit floating point. So that is basically the concept of processing, which we are not here into. So torch dot double, and if you take the similar example consisting a matrix of ones using torch dot float. Okay, so you see it will return you the same output in both the cases. Only the except difference is that here you have used torch dot double, so it is giving you a 64-bit floating point. Here you have used dot float, so it is giving you a matrix of ones, but it's a 32-bit floating point. Okay, so depends upon the what in certain applications the bit plays a very important role. And the example what I have taken, is uh, creating a random like matrix. Okay, just what and with the data type dot float. Okay, so if let's put up, let's run all this stuff again, so you can see it has been created. Okay, so it was 5 by 3, 5 rows and 3 columns, 5 rows and 3 columns. Again, here also there are 5 rows and 3 columns. Okay, though in the argument I have not specified the number of rows and columns. As an argument, I have prescribed only x. Okay, so since I have prescribed only x, so it will automatically take the 5 by 3 size of the matrix. So result you see has the same size of 5 by 3. So even if you are not specifically mention the argument, it is taking that feature from the input argument. Now since the input argument is x, which is already there, which was already there in 5 by 3 form, so it has automatically taken it in 5 by 3 only. Though I have not mentioned the size of the matrix specifically here. Okay, if you want to print the size, just to check, it will come 5 by 3, that means 5 rows and 3 columns. So torch dot size will just tell you, if you at any stage of coding or any stage of writing, if you just want to see the size of an array, dot size would help. Okay, and it will give you the answer in the form of tuples. So there are many data types, data formats when we talk about Python, like dictionaries we have, sets we have, lists we have, tuples we have. Okay, so if you see the format here which is presented is the form of tuple. Even if someone of you doesn't understand about dictionary, sets, tuples and all this stuff, don't worry, you can just ignore this. Okay, I'm just highlighting this here for the knowledge purposes. Now, certain functions that we can perform. Okay, let's say for example, I want to addition function that I want to perform. So let me define another matrix y, another array y, with random numbers, and it's a 5 by 3 matrix. Okay, so because earlier also we had a 5 by 3 matrix, like x was already there. So let's print y. So you can see this is y matrix, which has been randomly, values have been randomly created, a 5 by 3 matrix, 5 rows and 3 columns. And I want to add x and y. Okay, x is already defined above. X we have already defined here as well. So the latest x values will be taken. So let's run this. And now these values are the addition of x and y. So y, this has been created, x, this was there. So the values are right there. Okay, so x, y plus x. That's what we have, what we are trying to do. Okay, so similarly, this is how x plus y, that's been addition. If you want to do without using any plus sign, so you can use dot add functionality also. So using dot add functionality, again it will yield you the result by adding it. Okay, you can see result is exactly same. Okay, if you want to print x values here also, you can print x values here as well for clarity. Okay, let's do this. So these are the x values. Now since we are doing random, so values will change every time you will run. Okay, so these are the x values. These sorry, y values. These are the x values, and this is the values after doing the matrix addition. Okay, and similarly, if you want to add matrix using dot add, you can use dot add functionality also, and in the open and closing parentheses, you can mention that those two matrices which you want to add. So x, y I want to add. So if I run this, addition is there. If you see, the result is exactly same. Okay, these are the addition figures after using plus command, and if you use dot add, this is again giving you the same output. Okay, and then we can also provide an output tensor as an argument. Let's say, for example, Let me create a variable x or an array, sorry, a variable result or an array by the name of result, and it's an empty array. Empty means I'm drawing an uninitialized matrix. Okay, so let's run this. So this is an uninitialized matrix. So as I told you, in case of uh, uninitialized matrix, all the values which are there in the system will be taken. So I'm taking a torch.empty, an empty matrix. Dot empty means you are calling an uninitialized matrix. So whatever values are there in the memory at that point of time will be taken as the output. Okay. Now I want to add. Okay. I just want to add. So dot add x and y. Now what I'm okay. Let me remove this command for just for a second. Okay. Now what we have done, we have created an empty matrix, uninitialized matrix. I'm not printing the result because I don't need it. Still, if you wish to see, let me print this for you. So print result. Now, as I said that dot using dot empty, you are creating an uninitialized matrix. So whatever values would be there in the memory at that point of time, okay, will be shown as the output. But I don't want to do this. What I want to do is this. I want to use uh, the output tensor as an argument. Now, how it happens? I have defined first. I will define an input empty array of size 5 by 3. Okay, by the name of result. Okay. Now, what I want to do, I want to add x and y. So I will say toss dot add. I want to add x and y, and the output of addition of which I will get by adding x and y. I want to put it in the result matrix, the matrix which I have just defined above. So what is happening now? We have first created an empty matrix. Okay. Then we have performed an additional operation by adding the x and y matrix values. But the output of addition of x and y I want to show in the result array which I have created above. So what I am doing, I am providing an output tensor as an argument. So result is my output tensor. I'm giving it as an argument telling that whatever are the results of adding x and y matrix, show it in this particular output tensor. Okay. Now since it's an empty tensor, it's an uninitialized tensor, it will take the values and will print the desired result. Now you can see the values are exactly same, the addition values, but now they have become the part of the result array. So we have given the output tensor as an argument. Now this is again how it can happen. Okay. Then another way is in place addition. So in place addition means instead of writing torch.add, you can use the name of the tensor itself. Like for example, I say y. This is the name of the one of the tensor I want to add. So y dot add then underscore, and in the opening and closing parenthesis is the x. Okay. So I want that now this will tell the application that I want to add y and x together. So y dot add underscore, and the name of the second matrix would be in opening and closing parenthesis. And if you print this, it will yield you the same result. Okay, this is in place addition. So you don't need to use dot add or plus command. You can simply use the name of the two matrices or the two arrays you want to add, and in between it would be add underscore functionality that you have to use. Okay, so this is how uh, the operations we can run on matrix in different ways. Like I have taken the example of addition here. Okay. So in the next section, we'll be talking few other things of resizing and reshaping a tensor. Okay. So if you want to reshape your tensor, you want to resize your tensor, how we can do that. So that we would be discussing about. And then we'll be discussing a concept of NumPy bridging. And we from there, uh, these basics would be done, and we would be coming to the core concepts of deep learning. Okay. So all the best and happy learning. All right. So, this session probably would be the last session to cover the basics of PyTorch or uh, how PyTorch and NumPy go hand in hand. So now, next thing that we need to do is how to index uh, a particular array or a particular matrix. Okay, so if you want to see a particular column or a particular row, how we can do that? That's what we need to see. Before that, just for clarity, there are certain scenarios where I have used underscore after the function. So underscore helps you in mutating the tensor in place. That means the last array which was printed in your notebook. So using underscore will take or will mutate or will copy the last tensor or the last array as it is. Like for example, when I'm saying y dot add underscore x, so it will automatically take the uh, last printed x array value here when you are writing this add code. So the purpose of putting underscore after the function is only to tell the application that they have to mutate the last printed value. Okay, so now let's come to indexing. Okay, uh, indexing in Python starts from zero, left to right. Okay, so let's say for example, if we are talking about this particular matrix, so this is 0, this is 1, this is 2. Okay, 0th column, first column, and second column. In the similarly, when we talk indexing in terms of row, so this is 0th row, this is first row, this is second indexed row, similarly third index row, fourth index row, and so on. Okay, so the index doesn't start from 1. Okay, indexing starts from 0. Okay, that's important. Row wise also, column wise also. That's how the system in Python goes. Now let's say let me print x first. Okay, let me remove this command. Let me print x. Okay, now these are the x values we are having currently in our system. Okay, and now I want to see only particular values. I want to print only particular values of the x matrix here. So now what I have done, I have mentioned first argument as the colon. That means colon means I want to take all the row values. The first argument will represent the number of rows. So when I'm using colon as the first argument, that means I'm telling the application that you want to take all the rows. You are not supposed to ignore any row value. And then the second argument after the comma is 1. That means you have to take column number, column which is indexed at one position. So as I told you, the indexing in Python starts from 0. So this is 0th column. This is first column. Okay. So that means you want to print the first column and all the rows means all the values would be printed. So if you run this command, you can see the first column values have been printed. Minus 1.3703.0809, 0.3491 and minus 0.0217, 2017. So these are the first column values. Okay, so I have indexed this and I want to see particular figures only. So I have tell the system that you print me the first column and all the rows. All the rows means I have mentioned colon here. Colon means that none of the rows would be ignored, all the rows would be printed. So this is how you can simply index an array or a particular matrix as per your requirement. Then another way of resizing and reshaping is to use dot view command. Okay, and let's say I'm creating a random array of 4 by 4 size. Okay, and now once this array has been created, I want to change its size. I want to reshape it or I want to resize it. But before you go into resizing and reshaping, uh, there are two important things that you need to know. Here I have used .rand n. If somebody of you have noticed, earlier also in one of the commands, instead of using rand, R-A-N-D, I have used R-A-N-D n. Okay. Now these are two different commands in Python. When we talk about rand n and when we talk about rand, now if you are using rand n, which is more considerable when we talk about neural networking, uh, because it generates samples from the normal distribution. Okay, so when you are using rand n functionality, it will generate you the samples from normal distribution. That means this distribution will have two essential features, and that two features would be mean 0 and variance 1. But if you are using .rand, it will pick values from uniform distribution. Uniform distribution means the values would be picked between range of 0 and 1 only. Now, ideally, what happens when you are doing neural networking? Uh, if you will use normal distribution values, your and the normal distribution values will return values within range of 0 to 1. So there would be a lot of difficulties, or you will face a lot of difficulties in gradient calculation, or in weights assignment calculation, because zero value is very small. Okay, so uniform distribution is not supported, but it's not advisable. I will not say supported, because if you are using uniform distribution, then you have to reduce the range of your neural network as well. Why you have to reduce the range of your neural network? Because if you are using uniform distribution values, that means values between 0 and 1, and your neural networking range is very high, or the model range is very high, it will definitely generate errors. So it is not advisable. So it is always advisable that whenever you are generating samples on random basis, use rand n, means samples generated on the basis of normal distribution. Okay, so that is why rand n is more used for high range networks. Okay, but if the range of your model or range of network lies between 0 and 1, or nearby 0 and 1, then it's perfectly fine. You can go with the rand function as well. Okay, so that's the difference between using rand n and rand. So these two functions can be used with torch as well, with numpy as well. So for example, I have created a 4 by 4 matrix here, and I want to change its size. Okay, I want to reshape it to 16. So I can do that. Let's say, let me print X here for you for better clarity. Okay, let's print this. Now, first a 4 by 4 matrix was required. That means 4 rows and 4 columns. So this is the 4 by 4 matrix. X has been created for you on random basis. Okay. And since I have random, so we believe that these are normal distribution values. They will have mean 0 and variance 1. Now I want to change the format. I have used x dot view. Okay. Let's see how the shape has changed. So let me print y. Y is actually equal to x only, with the only difference that the shape has changed. Now if you can see, it has 16 columns. Okay, now the rows are gone. The it uh, the it has been divided into 16 column values. So first figure, second figure, third figure, fourth figure, fifth figure, sixth figure, seventh figure, and so on. So 16 columns have been created. So size have been changed using dot view. Okay, and similarly, let's say print z, another type of matrix that we want to create from x only, just changing the shape of the x, nothing else. As you see, this is has been created using -1 doesn't have much significance. -1 simple means you are inferring some other dimension. So now you see 8 columns have been created: 1, 2, 3, 4, 5, 6, 7, 8. Okay, and since as far as rows is concerned, I didn't mention particular rows, I mentioned -1, so it will take it automatically. Okay, so if even if you will say -1 here, that means you're inferring some other dimension, doesn't matter, it will give you the columns as per then according to its own application. Suppose I use 3 here. Okay, sorry, uh, for a 16 matrix, 3 by 8 is not possible. So only 2 by 8 is possible, because there's 16 values, so they can be divided at most in 2, and I want 8 columns. So for 8 columns, 16 values can be divided in 2 rows only. Okay, so that's why I can at most prescribe 2 rows. If I as -1, that means I am asking the application to decide itself how many rows are viable. So application can do that and will give you 2 rows only. Okay, so you can do this way also. So instead of you deciding the number of rows, because sometimes it get confusing to calculate. Like for example, here there were 16 values. Now I want to convert it into 8 columns. Here there were 16 columns. So let the application decide what should be the right number of rows. So prescribing -1 will help you with this. The application will automatically decide the right number of rows that should be present in your matrix. So using dot view, we have resized or reshaped our existing tensor again and again. So this was our original tensor. First we resize it to a 16 values in a single row, 16 columns, and then we further resized it into this format. So you can resize it any number of times using dot view command. Clear? And if you have a one element tensor, that means it has only one element. For example, I want to create a tensor torch.random only containing one element. So I can print it. Okay, so this is consisting only one element for me. In case of one element, you can use dot item functionality also. So you will get this value as a Python number. Okay, so here it is in the form of an array. If you want to print it in the form of a Python number, you can do that. You have to just use dot item. Okay, and this way there are hundreds and hundreds of operations. My idea here was to give you an influence of how the tensor system or the system actually works. And the best way of prescribing is to understand it with reference to matrix creation or by comparing it with the help of NumPy. Okay, because the way you apply functions in NumPy, the similar way you can do with Torch as well, with a little difference in command names. The command names in Torch are slightly different. In NumPy, we might use some different words. In the similar, there are lots of other operations that can be done, from transposing to indexing to slicing to mathematical operations and random numbering and so on. So you can go on this link, and if you just want to check it out, just check it. Otherwise, since we are into deep learning in this session, that means our idea is to understand neural networking in deep learning. This much knowledge is good enough to exercise PyTorch. Okay, but for all those enthusiastic learners, this is the link they can definitely go for. So this I have already explained. NumPy bridge is the just like conversion that you want to do from Torch to NumPy or from NumPy to Torch. That's one of the most simplest things that we can do. For example, I have created two matrices here. So one a matrix A, which is a matrix of ones. Okay, so it will contain all one values, and then a matrix B. Okay, so which is now B matrix is nothing. I want to convert this torch into NumPy. So I can use a dot NumPy and open and closing parentheses. So conversion from torch to NumPy is very simple. Simple, the name of the matrix you want to change, followed by dot NumPy and open and closing parentheses. So this will convert your torch sensor into your NumPy array simply. Vice versa is also very easy. Okay. So let's say, for example, uh, let me change a little bit of array here. A dot add underscore one. Okay, let's see what happens. Now, if you see, add underscore one means one would be added to every element of A. Okay, so my A tensor was one containing one values, and I'm saying add underscore one. So it will add one value to the existing A matrix. So the tensor will change to 2. Okay, so now the values are not ones, they are twos. Similarly, if you will print B, the changes will happen in B also, and there also instead of ones you will see the value twos. Okay, so simple operations that you can run very easily. Now this example is converting NumPy to torch. So let's say I'm creating a array of ones, okay? And once I have created an array, I want to create an array B by converting a NumPy into torch. So command is very simple, which I have explained earlier also. Torch dot from NumPy, and you want to convert this A array into the torch by the name of B. Okay. So very simply, you can simply do that. Okay. So let me remove this command for the time being here. Let's print this. So you see, okay. So this was the NumPy array with you, and then you have converted into torch. So a tensor has been created consisting of the same values. Okay. So I printed both just for your purpose. If you want to make certain further modification here, like for example, I'm using dot add. Okay. So I want to again I'm giving a output tensor as an argument. Again, we have taken an example above also, where I created an empty tensor first, and then that empty tensor was given as an argument. Okay, giving output tensor as an argument. We have discussed one example above as well. So this is a similar example. So I'm simply naming my existing tensor, which is existing array, which is a NumPy array. Okay, and I want to create an output. This a array has been given as output as well. So let's say, for example, let me take it. I can see mp.add means it. I'm asking for addition, and I want to add 1 to every element of a. Okay, I want to add 1 to every element of a. Now a was having values of ones, 1 1 1 1 1. So 1 would be further added, so the values would be changed to 2. Okay. Now I don't want to create a fresh matrix. I want to do all the modifications in my existing A. So I have given the output A as a argument. So that's why a new fresh matrix is not supposed to be created. So whatever modification is done would be done in this earlier existing matrix. So this is how this happens when you give your output tensor as an argument. One of the examples we have taken it above also. So whatever modifications would be done in the existing tensor. A new tensor will not be created. Okay, that's the underlying difference. Now since we have talked about this, now this portion is just for knowledge purposes. Since we have talked about that the ideal one of the very popular application of tensor is that it can work with GPUs as well. Okay, so if suppose a GPU is available like CUDA library is available, then it can be done. Okay, so now what if now this is only if CUDA library is available, like if you want to work with a GPU. Okay, so you can use torch dot device to move tensors in and out of GPU. So if you want to transfer your tensor to the GPU, torch dot device can be used. Similarly, if you want to take your tensor out of GPU, that can also be done. Now CUDA or CUDA is uh, found by NVIDIA. Okay, NVIDIA is there who has formed this GPU. So this is the command that you need to run. So if torch.cuda is available, then device is equal to torch.device cuda. So that means I'm creating a cuda. I'm talking about a cuda device object. Okay, and I'm creating now an array y. Okay, so now this command will directly create a tensor on the GPU itself. Okay, so like for example torch.ones, I'm creating a tensor of ones. Okay, and I want to and I've given additional argument device is equal to device. So this will directly create a tensor on GPU. So if a GPU is running on your system, okay, like for example CUDA CUDA I have taken as an example. So it can be done. You can directly create a tensor on the GPU. First, you have to call the formed a variable device and call the command torch.device and the CUDA tensor. So calling a CUDA device. Then you can create a matrix or an array right there on the GPU using uh, two arguments. One, the name of the matrix, and second, the device equal to device, which we have defined here. Then x dot 2. Okay, so instead of creating a tensor on GPU, you can transfer it to the GPU as well. So dot 2 can be used for transferring it to the GPU. So dot 2 and then the open and closing parenthesis, you can the device is the additional argument. Device is nothing, it's the CUDA device object that you have created. Okay, this is the CUDA device object that you have created, which you are mentioning as an argument here. And then you can perform whatever functions you want to do. Okay, so for example, you want to do addition of x and y, you can do that, no issues, and print the required command as well. I can't print the output here because GPU is not available on my system. So what I am doing it on the basis of my CPU, not on the GPU. But for all those, if GPU is available, it can be done. Now since it is not available with me, I'm not running this cell. Okay, but that's a very simple command. You have to first give an if loop, if command, to check if it is available. So if dot CUDA is available, then I will create a CUDA device object. So I'm creating a CUDA device object using torch.device command. Then there are two things that we can do. Either we can create the matrix directly on the GPU. So using torch dot, let's say for example, I'm creating a matrix of ones. Okay, and these are the two additional arguments I need to prescribe. One is x, and second, device is equal to device. Then I'm creating another x tensor, and I'm using dot to functionality. Now this will uh, transfer my tensor or move my tensor to the GPU. So the earlier case, I have created directly a tensor on the GPU. Here I am transferring a tensor to the GPU, or I'm moving a tensor to the GPU, and then performing the whatever desired function I want to perform. Okay. So that's it. But this cell I cannot run because CUDA is not available on this system. So there is no point of running it. But for your knowledge, I'll just let you know if GPU is available, how you can move a tensor in and out of the GPU. Okay. So that's all about the basics of PyTorch. Okay. So these basics I wanted to cover certain basic words, certain basic terminologies, make you understand how you can create matrices or arrays using PyTorch, and to make it more easier by giving you a comparison between the NumPy and the PyTorch functionality. So I believe that after looking into this, you must have seen that it's more or less same when we talk about NumPy. Only little bit difference of commands is there. If you want to create array using NumPy, a little bit command is different. If you want to create using Torch, little bit commands are different, but outputs will go exactly same. Okay, so that's where I wanted to build your thought process of what you are working with. Okay, so now I feel that there have been sufficient understanding in your heads that what we are talking about when we are talking about PyTorch. And from now we will move on to into the core deep learning. Okay, but it's important for us to understand the concept of tensors and the functionalities, because whenever we talk about deep learning means application of these concepts in the area of computer vision or images, the data is present in the form of matrices only. Okay, now since the data is present in the form of matrices, it is very important for us to understand how the concept of arrays or building of arrays work. Okay, so that's all for this session, and now we would be next session we would be first going into the theoretical understanding of deep learning, how the system work, how the concept works, and definitely followed by certain practical examples. So till that time, keep yourselves fresh, keep practicing, and keep remain focused. Okay, thank you so much. Hi. So now it's time to enter into the core understanding of certain terminologies or major terminologies like machine learning, deep learning, and how the two are different. Now, when we talk about machine learning, uh, and this field continues to evolve as one of the most in demand and promising career paths, and not today, perhaps for even next decades to come. If we really see and try to visualize the most important skills that are required in next decades, so we can take it the way uh, there would be demand for people who can uh, who are really able to take data, who have the skills of collecting data, understanding the data, making transformations and manipulations to it, process it, extracting value out of it, finally to visualize and communicate it to the stakeholders. So we can precisely say into the what is known as ETL, that is extract, transform, and load. Extract the data, transform, manipulate, or wrangle the data, and then finally load it to visualize or to communicate it to the respective stakeholders. Now, typically, when we talk about machine learning, which is a subset of artificial intelligence, so here I believe that another important thing that you need to understand is the difference between artificial intelligence and machine learning. Now, artificial intelligence in a simple language means giving human brain or installing human brain and understanding to the machines. One of the most popular examples that we can think of is the concept of driverless cars. Now, the driverless cars concepts is very simple, which says of making machine capable of understanding and making decisions like a human. Let's say, for example, if it's a red light, you know it, you need to stop. Uh, as a human, you have the understanding of making a decision whether you need to uh, uh, you know uh, uh, cross paths or not, or whether overtaking should be done or not, or on green you need to move on red light, and so on. So all these human understandings, we want to install it in the machine. That is basically artificial intelligence. Artificial intelligence means making machines capable just like humans. When we talk about machine learning, which is ideally considered to be a subset of artificial intelligence, machine learning is more concerned about building models based on certain historical data. So you have a historical data. Historical data means data which has already occurred in the past. So it might be 1 year data, last 3 year data, last 5 year data, last 10 year data, and so on. 3 year and 5 year data is is considered to be most appropriate. So now what you want to do, you have a historical data with you. On the basis of that historical data, you want to build models. So before you build a model, there is an essential step that needs to be done, which is dividing your historical data into training and testing. So we have two subsets of historical data. One is the training data, the other is the test data. Now, training data is that portion of the data which shall be used for the purpose of model building. So that means whatever model I am trying to build will be built on the basis of that portion of data. And once the model has been built, it needs to be tested, it needs to be validated. Now that testing is done on the basis of test data. Okay, let's say for example you have 10,000 records in your data, so you divide it into, let's say, 80/20. So that means 8,000 entries would be, or 8,000 random records would be used for the purpose of building the model, and the remaining 20 2,000 records would be used for the purpose of testing the model. Okay, so there would be no replication. That means the records which would be present in the training data would not be in the test data, and vice versa. So that is testing the model using test data. And finally, once the model has been tested, once the model has been validated, it's time to trust the model and use this final model for the purpose of forecasting. Now, this is simply how we can understand the concept and the usage of machine learning. So if we talk about Artificial intelligence is enabling machines to think like humans. Then machine learning, which becomes the subset of artificial intelligence, means training machines to get a better at a task. So so you can take better performance for the machines. Machine learning is identically a very important part of predictive analytics or making predictions. And then finally, deep learning, which is a part of machine learning, a subset of machine learning, means that now you would be using multi-layered networks or neural networking for the purpose of machine learning. So when you enter into the usage of neural networks or multi-layered networks for the purpose of machine learning, that means you are going into the process of what is known as deep learning. Okay. So we can say that artificial intelligence is concerned with intelligence in computers, okay? Human intelligence, giving them the human brain, yeah, giving them the human decision making, giving them the human understanding. While data science or machine learning or or deep learning is more about using the data for the purpose of gathering insights. Okay, because once you get the insights, you try to understand, you come to know that how or what repercussions this data has in our decision makings. Effectively, one of the very prime things you need to understand is the difference between machine learning and deep learning, because this course is more about deep learning. We are going more towards the deep learning. That means we would be using neural networks or we'll be using multi-layered networks for the purpose of our analysis. So these are the few important points that you need to understand. Point number one. Now, machine learning works with different amounts of data because we are into model building process. So we need uh, different sorts of data or quantity of data that needs to be divided in the training and the testing. So mainly if the data is small, now small data means 3 years, 5 years, 10 years, we consider it as small only. So if it's a small amount of data, we use machine learning. Okay. But if the data increases rapidly, then deep learning is considered to be better technique because it gives you the results with high efficiency. Now what is small amount data, what is high data, what is big data? There are no official definitions to that. Let me make you this very clear. The big data, now this word has been very popular in these days and probably days to come, but what we all need to understand that there are no official definition to these words. Nobody, there is no official definition what is big data or at what point you should say that this data has been now changed into big data. No, there is no definition of small data. As an analyst, it is your decision that whether you consider it as a huge complex data or not. If you think that the data is too large, too complex, maybe complicated, lots of variables are you know uh, you know uh, juggling over each other, then we probably deep learning is a better technique to go for. Then deep learning algorithms, they have been designed to heavily depend on high-end machines. So if you are using deep learning process, if you're going into deep learning algorithms, then you have to be particularly very choosy to the fact that high-end machines are required. If you go for machine learning, even traditional machine learning algorithms are good enough. So you really don't need to, uh, depend too much on the higher end configurations of your machine. Now, deep learning algorithm typically depends upon the concept of matrices. That's why when I started off this discussion on PyTorch, I gave you the uh, very my first idea was to give you the introduction to the system of matrices, building matrices, performing operations on matrices, and so on. So the reason was that the entire deep learning algorithm, it's totally based on matrices, and matrix multiplication is one of the prime concept that is used in deep learning. So large amount of multiplication takes place in the background, and obviously when such large amount of matrix multiplication is going on, that means hardware requirements are also huge. to store that data. Other difference that we can think between the two is in concept of feature engineering. Now, feature engineering means putting the domain knowledge into the specified features. That means you want to convert the textual or the domain knowledge into the form of features so that the complexity of the data can be reduced. What do we do? What is the benefit of doing it is we, with the help of the features, we try to understand the patterns. We try to make patterns based on our data. Now, these patterns are visible to the learning algorithms and help in better data analytics and uh, efficient efficient analysis, what I will say. So, one of the prime application when we talk about uh, uh, deep learning is that its application or its uh, the process which is involved in the background of converting domain or textual knowledge into specified features, and these features then can be changed into patterns or help in making patterns which are visible to the learning algorithms. Let's say, for example, when we talk about traditional machine learning. Now, traditional machine learning particularly focuses on pixels and other attributes which are required for feature engineering. Now, feature engineering is there in machine learning as well, but the feature engineering happens on the basis of pixels and other smaller attributes. But when we talk about deep learning, now, deep learning algorithms, since we are talking about neural networking, we are talking about multi-layered architecture. So deep learning algorithms, they focus on high-level features from the data. Now, when we talk about high-level features, because we might be entering into the world of computer vision, image processing, and so on. So high-level features are required. Let's say you want to predict what type of image it is, or what let's say there are lots of images of animals, and you want to see that to which animal this image belongs. So this require high level feature orientation. Low level feature orientation or pixel level feature orientation will not work. So you need high level feature orientation, and so that your model can understand these features and can make the prediction. So it reduces the task of developing new feature extractor for every problem. You don't need a new feature extractor for every problem. The algorithm itself is capable enough to perform it in one single go. Okay. So though deep learning is the subset of machine learning or is a part of machine learning or is a type of machine learning, you can say, but in terms of dealing with complex data, huge data, or complicated data, deep learning is more efficient and more successful. Ideally, because of two three important reasons. One, that it believes in feature engineering, okay, based on high level of features. So it focuses on high level features, not on the basis of pixels, because machine learning focuses on pixels and other attributes for future engineering process, which is on the lower side. But deep learning, since we are talking more about complex data, so high level features are focused in case of deep learning algorithms, and that's why the results are more efficient and better. Okay, and uh, further, it's totally one of the prime important thing we need to understand that in deep learning, hardware support is required. A huge hardware support might be required because in the background there are lots of matrix multiplication operations are going on. So to store that, it's very essential. Okay, so these are few underlying differences that you need to understand between these two important terminologies. One, the deep machine learning, and second is the deep learning. So from now on, we would be focusing on deep learning, understanding how the system of deep learning works. Okay. So this session was more focused on understanding the concept of machine learning and trying to understand the differences between the two important parts, the machine learning and the deep learning. So I'll meet you in the next session. Till that time, keep practicing and happy learning. All right. So last session we have been focusing on the differences between machine learning and the deep learning. Though ideally, deep learning is a process of machine learning, is a part of machine learning, but it is considered to be more efficient and more effective when it comes to dealing with the complex and complicated data. Now, the word deep learning is basically based, or the concept deep learning is based on what is known as neural networking or neural architecture. Now, it gets it, it's this word gets its motivation from the human brain because the way human brain is designed, it's in the form of neural networking only. The networks attached to each other neurally. So we believe that when we talk about a neural architecture, when we talked about neural networks, they just are in the same form as the human brain. So when we discussed about machine learning, I told you that there are few essential steps that need to be taken. So you have a historical data with you. That historical data needs to be divided into training data and the testing data. The training data is that set of data, or that proportion of data which is used for the purpose of building the model. And then the remaining proportion acts as the testing data on which the model that you have built is tested and validated. Once testing and validation has been done, we can use the model for the required purposes. When we talk about deep learning, again, deep learning has its own steps, somewhat similar to machine learning in terms of ideology. The very first step is building a data pipeline. Okay. Now, when we talk about pipeline, now pipeline helps in automating the entire workflow. So whatever workflow is involved in the deep learning or in machine learning, with the help of data pipeline, you can automate the entire workflow process. Now, the pipeline it operates by enabling a sequence of data to be performed and correlated together in a model. So a model is created. Pipeline is just acts like a model in which we mention the entire sequence of workflow or entire sequence of data transformations that need to be done. And once you call the pipeline, all the transformations will take place, or or the entire stages will take place automatically, so that the required testing and evaluation can be done. Okay, so that's where the pipelines help. They help you in automating the entire workflow or the stages involved in a process. You don't need to perform them manually one after the other. So building a data pipeline which will help you automate your entire workflow process, whether in deep learning or machine learning. Then building the network architecture, followed by evaluating the architecture using a loss function. And then finally, optimizing the network architecture or the diagram weights using an optimization algorithm training. Now, weight optimization is a very important process in neural architecture or the network architecture. We will be discussing about this entire process later on in detail, that how this entire concept works. Okay, so for the summary, you can understand that these are the four essential steps: build the pipeline, automate your task, build the network architecture. Then once the architecture is there, evaluate it using a loss function. Loss functions will come later on. And then optimizing the weights that are involved in the architecture with the help of an optimization algorithm. Okay, so if you can see this diagram in front of you, it's very simple. Now there's an input data, and then these are the layers, the layers in which the required transformations are performed. So there are weights and gradients involved. We'll discuss about these concepts later on, how these works. So these are the transformation layers, one after the other, in which the entire transformations or the required transformations will keep on happening, followed by an optimizer, which will help in optimization of the architecture, the weights which are involved in this architecture, and there is a loss function. Okay, now the accuracy of the model or the architecture is evaluated using a loss function. Okay, so when we talk about optimization of the weight, the accuracy evaluation is very important, and that can be done with the help of loss function only. Okay, so ideally we can say that when we talk about a deep learning algorithm, it involves getting the input data. Okay, on the basis of input data, building the required architecture, and within this architecture you can find bunch of layers. For example, in this diagram there are two layers in front of you, so bunch of layers which are embedded in them. Okay, detail we would be talking about later on, how what these things are and how we use them when we are developing our neural architecture. So now let's enter into the process of deep learning, okay, and see how the entire system of deep learning works. So we'll start with the concept of deep learning, and what it is, what are the essential steps in detail or the procedure in detail, that how the entire precision of deep learning works. And we'll be further going on to what is known as forward propagation and backward propagation. And from there on, we're moving on to the optimization process and the accuracy process. And lots of stuff needs to be done. So till that time, keep revising, and because revision is very, very important part of learning, so that everything goes hand in hand and there is nothing uh, you know lagging behind. So happy learning, and I will meet you in the next session. Hey, now it's time to accelerate your level of excitement, because now we are entering into understanding deep learning in detail. So let's start. Now let us first understand what it is. Now ideally it is a branch of machine learning which is totally based on what is known as artificial neural networks or neural architecture. One of the other differences which you can think of between machine learning and deep learning is that machine learning is applied to both types of data. So machine learning can be applied to supervised data also, means labeled data, and it can be applied to unlabeled data, that is unsupervised data as well. But when we talk about neural architecture, when we talked about deep learning or neural networking, it specifically applies to the area of supervised data or supervised learning. So that is one of the, again, one of the prime differences that you can understand between machine learning and deep learning. So it's again like a mimic of human brain. You're trying to create a mimic of human brain that is learn by example, learn by experiences, learn by observations. So you don't need to explicitly program everything. Okay, so you give the input and explicit programming is not required. There is no need of developing a feature extractor every time. Then it is one of the key logics behind driverless cars. So in today's world, when we talk about cars, where no drivers are required, machines will make the decision of running the car, like enabling them to recognize a stop sign, green sign, red light, how to overtake, when to overtake, not to overtake, to distinguish a pedestrian from a lamp post. So these are very, very important features that we are trying to give to a machine in a driverless car. So deep learning is one of the prime technology or the key technology that is being used for this particular purpose, because one of the prime applications of deep learning is in the area of computer vision. Computer vision, so its machine can recognize the various elements in an area. So it is the key to voice controlling consumer devices like phones, tablets, TVs, hand-free speakers. So again, deep learning exists here as well. So these are some of the common examples that exist around us, probably in our daily life, but we don't know that what's happening in the background. So ideally, now you know that it's basically the deep learning technology which is happening in the background and giving you that level of features or the facility. Now, ideally, this is a typical diagram of a network architecture. So as you can see, there is an input and then there is an input nodes layer. Okay. So With the help of these input nodes layer, the data is fed to the architecture, and then there are certain hidden layers. Now the entire process of feature extraction takes place in the hidden layers. Okay, so once the input has been fed to the architecture with the help of input nodes layer, then whatever feature extraction process will take place, because ideally the concept of deep learning is based on feature extraction, high level of feature extraction. So all that feature extraction process takes place in the hidden layers, and once the feature extraction is done, then the output is collected and reflected through the output nodes layer. So this is a typical way or a procedure in which the network architecture, the neural architecture works. So a computer model learns to perform classification tasks directly from images, text or sound. Let's say for example computer vision. Let me show you a diagram here. Yeah. So now, for example, this is the road, okay, and there's a traffic light on this road. There's a person or pedestrians as well. There are people, lots of people around. Then there are cars on the road. There are trucks on the road. There are traffic lights, and uh, the different people are carrying different things in their hands. For example, lady in the left might be carrying a handbag, and so on. Now, deep learning, one of the prime application of deep learning helps in the is in the field of computer vision. That is recognition of images. So suppose you are driving a driverless car. So this deep learning technique will help the machine in understanding, in recognizing different images that are there in front of it. So with the help of computer vision, with the help of deep learning technology in the background, the machine will be able to understand that these are the pedestrians, these are the people, this is the red light, these are the truck, there is the car on the left, right, and so on. That is image recognition or computer vision. So let's come back. So it's the computer model that will learn to perform all the classification tasks. That means it will, with the help directly looking at the images or the text or the sound, it will recognize where to place whom. It gives you the state of the art accuracy and sometimes exceeding the human level performance, because humans are drawn by emotions. Machines don't have emotions, so they are highly logical when it comes to that. They look logically, they see everything rationally and logically. Emotions and disturbances are not involved. So models need to be trained by using large set of labeled data. So as I said that one of the prime differences between machine learning and deep learning is that the machine learning can be applied to supervised data, that means labeled data, as well as to the unsupervised data, that means the data which is not labeled. But when we typically talk about deep learning, in deep learning, the models are required to be trained by using a large set of labeled data only. Let's say, for example, when we talk about driverless cars. So when you are developing a driverless car, then it requires millions of images, probably thousands and hours of videos of driving experiences of different people, with the help of which you are trying to make the machine learn. Okay, and then obviously there are neural network architectures that contain many layers, the input layer, and then there can be multiple hidden layers, and then finally the output layer. One of the prime reasons we are talking about deep learning is its substantial computing power. That's why the application of deep learning in the fields of is in highly complex and complicated fields like uh, image recognition, image processing, computer vision, and so on. Now, let us understand how the entire process of deep learning works in a step-by-step way. The very first thing that we know, and now we are very clear that it uses the neural network architecture. Okay, so now since it uses the network architectures, that's why deep learning models are often known as deep neural networks as well. Okay, now what is the meaning of deep here? Deep learning. Now, deep comes from the use of multiple layers in the network. As I've shown you a very simple diagram above, that it consists of an input layer. Then the hidden layers, which can be more than one, it can be 2, 3, 8, 10, 9, totally depend upon the requirement or the complexity of the data involved. And so that means it is using multiple layers in the network. So that's why we call it as a deep. Okay, that's where the word deep comes from. The third thing we need to know, that's an adaptive system. That means it learns by using interconnected nodes or neurons in the layered structure. I will not use the word neurons at regular intervals because neuron is more linked to human brain. So the node word would be more usable here. So it learns by using interconnected nodes which are connected to each other in the network architecture, and that just resembles like a human brain. That is why the word artificial neural network, from where the word artificial neural network comes. Okay. Then another important thing that we need to understand is that it learns from data. So that means the model needs to be trained on the basis of huge amount of data, and it can be trained to recognize patterns, images, processing images, classifying data, and predictions as well, forecasting of future events. Then, since it works on the process of feature extraction, so there is no need of manual feature extraction. Features are automatically extracted from the images, videos, and so on. Okay, so the relevant features are not pre-trained. Okay, they are learned while the network trains on a collection of images. That means pre-storing is not there. So once the network is getting trained, let's say for example on a collection of images, these features are automatically learned. Final thing that we need to understand, that there's a usage of layers. So now when we talk about neural network architectures, it learns to detect different features of an image using tens or hundreds of hidden layers. That's what I said, that in the diagram I showed you one layer, but it can be any number of layers. Now let's say now every layer has its own purpose. Let's say for example, the first hidden layer could learn how to detect edges of the image. Then the next layer can talk about the corners of the image or the middle of the image. And then the last probably will learn how to detect more complex shape involved in an image. So every hidden layer will have its own purpose. So no layer will have the similar purpose. If something is judged by first hidden layer, then the other hidden layer will look at the other part of the image or other features of the image and try to recognize it. Let's say, for example, now there's an input layer, then two hidden layers, and the output layer. So first layer might be looking at the edges and the corners of the image. The second layer might be looking at the middle portion of the image and try to extract the relevant features. Let's say, for example, there are facial recognitions that you want to make. So provide the input, then the first hidden layer might only look at the corner or the edges part of the image. Then the second layer might look at the more deeper features like shape of the eyes, color of eyes, nose, structure of lips, cheeks, and so on. And finally there's the output layer which will give you the desired output and will identify the image or the person to which it actually belongs. So that's how the entire system works. Every hidden layer has its own purpose and extracts own set of features. Let's say for this example, now there's an image that we are trying to recognize, the first image which you can see on the screen, and then this input layer, then hidden layer, it will start extracting features out of this image, and then it probably give the desired output. So can you tell me what should be the right output? Obviously it looks like dog. So ideally, the after the process gets completed, the output should give us the name of the image that it's belong to a dog. In the similar, if you look at the second image, the process will repeat again in the same manner. Input layer, input is fed, then there are hidden layers which will try to extract various features out of that image, and then finally it is fed to the output layer, and then probably output should be shown as that it is a cat. So this example image I have already shown you. It's a typical example of a computer vision where a machine is trained to recognize the objects around it. So from here on, we'll come on to the concept of forward propagation and we'll discuss in the next session. So this session, we have been more concentrating on understanding how the entire system of deep learning works. What is the concept of input layer? What is the concept of hidden layers? Hidden layers are not one, they can be hundreds in number, totally depend upon the size, complexity, and the critical nature of the data. And every hidden layer has its own purpose. So every hidden layer will work on feature extraction only. So one hidden layer might be looking at certain set of features, then the second hidden layer might be looking at some other set of features, and then finally there's the output layer where all the feature extraction would be combined, collected, and the output is returned. Okay, that's how the entire concept of deep learning works. So till the next session, I will advise you all to revise till here, because now from now on we'll be going on to entire deeper logics of application of deep learning. So we'll be going into coding now, and we'll be seeing how we can apply different concepts of deep learning with the help of codes. But before that, it is very important that you are absolutely clear till this stage, so that no confusion exists in anybody's mind. Okay, so thank you so much. Keep learning and keep practicing. Hi. So, after understanding how the system of deep learning works, let us go ahead and understand the working or the meaning of what is known called as forward propagation. Now, forward propagation is the process in which or how the neural networks actually make predictions. That's the basic uh, methodology which is adopted by neural networks or neural networking while making their forecasting or the predictions. Now, how it works is that whatever input data you're feeding it to the input layer is forward propagated. Forward propagated means is moved in one single direction, in the forward direction, with the help of a network layer by layer till the final layer, which outputs a prediction. So as I have explained to you earlier as well, that there can be a one layer, there can be more than one layer, there can be hundreds of layers as well. Totally depends upon the size of the uh, network architecture you are dealing into. So whatever number of layers we have, the input data will be propagated in forward direction through each layer one by one, okay, till the final layer. And this final layer is responsible for giving the output as prediction. So let's say we have a model. Let's have a simple assumption that if you have a model, so it could be a neural network, it could be some type of classifier, or it can, or you can, the best way of understanding it in the is in the form of a computational graph. Okay, just like a decision tree. So if you think of a computational graph, it is nothing. It's just a network of nodes. You can just think of decision tree. Now decision tree is nothing. It's just a network of nodes connected by branches. In the similar way, when we are talking about computational graph here, it is a network of nodes that and every node might represent a number, a scalar, or a tensor. And these nodes are connected to each other via edges. And these edges represent the functions or the operations that you need to run between the nodes. Okay. For example, you want to add two nodes. So the branches or the functions or the edges will act as the functions or the operation that you need to run on it. Okay. Just like for example, if you want to add two nodes, so addition is an operation which you want to run using those two nodes or the values which are incorporated in those two nodes, and that is represented via edges. Let's take a small example. For example, we have a graph, a computational graph having four nodes A, B, C, D, and then there are certain operations that we want to perform between these nodes. Like for example, we want to add these two nodes A and B, we want to multiply nodes C and D, and or so on. Our final job is to do all the operations until we get the final node or the final output G or the final result G. That's the graph we want to draw. So let's see how it looks. So as I said that let's say we have four nodes here A, B, C, D. Every node has its own value. A is equal to 2, B is equal to -4, C is equal to -2 and D is equal to 2. Now since we are talking of tensors here, we are going through PyTorch. So we believe that we would be working via tensors. So let's say A, B, C, D are the tensors that we have initialized. A is holding a value of 2, B is holding a value of -4, C is holding a value of -2, D 2. Okay. And now you want to run the operations between these nodes. Let's say you want to add node A and B. So that's an operation you want to perform. Okay. So let's add it. So you want to add these tensors. Okay. So add A and B to tensor E. So after adding these two values, their output will store in another tensor by the name of E. Okay. Similarly, we want to multiply C and D, these two nodes values. So multiplication is the operation that we want to perform between these two nodes represented by these edges. So 2 into -2 is -4. And let's say we are storing its value in another tensor known as F represented by this node. So after running the operations, now we have two more tensors, one tensor E and tensor F. In tensor E, the output of the addition of A and B is stored. In tensor F, the output of multiplication of C and D is stored. Now I want to run final operation. Okay, so we print the values of these tensors EF. Okay, now what do we want to do? We want to print the final, or we want to calculate the final value G. Okay, so we want to multiply the value of E and F. That means -4 into -2, that gives us 8. Okay, so there's a multiplication operation that is happening between E and F, and the value 8 would be stored in the final node, the final node named as G. Okay, so this is basically a computational graph that you can think of. This is what a computational graph looks like. Okay, so there's an input layer in which the input is getting fed. Then there are certain hidden layers where the processing is taking place or the operations are taking place. And then finally there's an output layer where the output of the prediction as a prediction gets reflected. Okay, so neural networks can be understood simply as a computational graph. Ideally, you can say that whenever you are running a neural network, whatever code you are putting it actually gets converted into a computational graph in the background, and whatever processing is happening in the background in the form of graph, and then final output is reflected on your screen. Okay, we have taken a very simple example here just for our manual understanding, but yes, since we are talking about complex data, we are talking about handling complicated data, so obviously in reality when you are taking such type of data, the neural network would be too large and too complicated, might be too complicated as well, because of the interconnections or the operations that you want to run between the nodes. Okay, so let me take you and let me show you on how to run this forward propagation on the PyTorch Google Collaboratory. So that's a collab notebook. Okay, so I want to first initialize four tensors, tensor A, B, C, and D, holding different values. So we have discussed the methodology earlier also. A torch.tensor, so I want it to hold the value 2. Then B torch.tensor, I want it to hold the value -4. Similarly C and D holding the value -2 and 2. Okay, so if you want to print a particular tensor, you can definitely see, like for example I have put in a print comma, you can print B also, any other type of tensor also, just to check. Otherwise this is not essential, that's not required as such. So I'm just showing you to make you understand that once you have initiated a tensor, you can definitely print its value as well, just for your own curiosity. Now we want to do two operations. One, we want to perform an addition operation between A and B, and store their output in the node E. Similarly, the second operation that we need to run is the multiplication operation. Okay. Now we want to multiply the values which are holding in C and D and store the value in F. So these are the two operations that we want to run. Fine. And final operation is between E and F, multiplying the values of E and F and then holding them in G. And finally, I want to see the value. So in this my case, I have printed the values of E, F, and G. If you want, you can print G only, the final result, your choice, just for clarity. And this is the tensor values you get, that your G is holding a value of 8 in the form of a tensor. Simply a very simple example of how forward propagation works, just to make you understand that everything happens in the form of a computational graph. Okay, so let's come back. Now let's see how the procedure actually happens in detail. Okay, now this was a very summarized example I have given you, but what happens in detail we need to understand, because once we'll move ahead, things will go little different. Now each node or neuron, now neuron is because we are talking about neural network, so actual word is neuron, just to avoid confusion, because neuron is a word which is attached to brain, we use the word node. So each neuron or node receives a multiplied version of input. That means input is fed to each node. The way we have in our example, we have fed input to node A, B, C, and D. And once the input is fed, then random weights are added or allocated based on certain uh, logic. Okay, so random weight which is then added with certain static bias value, and that is unique to each neuron. So weights would be taken, random weights would be taken, because till this point of time there is no logic or no certain clarity on the basis of which weights can be calculated. Okay, so manually it is not possible to calculate some optimum level of weight. So we need to specify random weights. Okay, what are weights? What is the importance of weights? I will come to it later on. So one, the first step is that each neuron, each node receive the input. That means input is fed to every node, and then random weights are allocated to each particular node. Now, then this is then passed to an appropriate activation function. Okay, there are different activation functions like sigmoid, ReLU. Every activation function has its own usage, but the sigmoid and ReLU are the two most used activation functions when we talk about neural networking. So once the input has been fed, random weights have been allocated, then it is passed through an appropriate activation function, which will decide. Now, what is the purpose of this activation function? This activation function will decide the final value to be given out of the neuron. That means what is the final value that should go out of that neuron, maybe passed on to the next layer or next neuron, is decided by the help of this activation function. Popularly, there are two activation functions which are normally used. One is the sigmoid, which is having an S sort of curve, S-shaped curve. Okay. Now, if you're using a sigmoid activation function, it will take on the input and it will map the resulting values between 0 and 1 only. Okay. And that actually is one of the disadvantages of sigmoid also. And then ReLU gives output between 0 and infinity. So the range of ReLU is very high, and therefore ReLU is more preferred in majority scenarios. So unless and until your input range is also very near to 1 or lies between 0 and 1, sigmoid is not very much preferred, because it starts introducing bias into your forecasting. ReLU, since its range is very huge from 0 to infinity, so it's ideally the most preferred activation function. The job of activation function is very simple. It decides the final value that needs to be given out of the neuron or out of that particular node. Once the output is generated from the first layer, now there can be many layers. Okay, so once the output is generated from the first network layer, Then there is a loss function which is calculated, and backward propagation is performed where the weights are adjusted to make the loss minimum. Now, if you read this first point again, so here I told you that random weights are allocated to the each node, to the nodes to which the input has been fed, and then it is passed to the appropriate activation function and so on. Now, since the weights were random, we need to check whether it has generated uh, an optimum result or not. Now, optimum result or optimum output means an output or a result with minimum error, with minimum loss. Okay. If the loss is very high or if it is not on the minimum side, then we need to make adjustment in the random weights that were allocated in step 1. Okay. Now, to adjust those random weights, backward propagation needs to be used. Backward propagation means reverse propagation from the output layer back to the input layer. Forward propagation means the uh, the the flow of data will be from input layer to the output layer, but backward propagation means the flow of data would be reversed from the output layer to the input layer. Okay, that's going in reverse order, so that weights can be adjusted in a manner that the loss or the error becomes minimum. Okay, and the calculation of loss is done with the help of a loss function. So the idea of backward propagation is to find the optimal values of weight, because when we started off this network, when we actually feeded the input to every node or every neuron, we have allocated random weights to it. There was no logic to that weight allocation. That's why we need to check the loss, the level of error or the level of loss which is there in the output. If it is very high, then we need to adjust the value of weights in a manner that the loss can be as minimum as possible. So that weight adjustment is done with the help of the backward propagation by moving the data from output to the input layer in a reverse order. So finding optimal values of the weights is what the entire process of back propagation focuses on. Now, what is the use of activation function? One, I told you that when you pass through an appropriate activation function, it decides the final value which needs to be given out of that particular node. Further, we can say that if the activation function is not applied, then the output will become a linear function. Okay, so if you are running a neural network or you are forming a neural network, or you want to do predictions using a neural network, and you are not using an activation function, that means you are simply running a linear regression with limited learning power. Now, linear regression, though, is most used, but it assumes that there exists a linear relationship between two variables. That means if you draw the graph between two variables x and y, then it would be a straight line. Linear means straight line. So if you are not running an activation function, that means you are actually working in the form of a linear regression. And linear regression, the very major limitation with linear regression is that it assumes that there is a linear relationship between two variables, which doesn't exist in real world. In real world, you will hardly find examples where perfect linear relationship exists between variables. Okay, that is why it is always preferred that either we go with sigmoid or we go with ReLU or some type of activation function which can give us better level of predictions with better accuracy and minimum loss. Okay, that's how actually the piece, in background, the process of neural networking takes place. So we have discussed this earlier also, that when we talk about network architecture, means the computational graph as a whole, it has an input layer where the input is fed. Then there are hidden layers in which the feature extraction process takes place. I've explained this in earlier sessions, what is feature extraction. Now, hidden layer can be one, it can be two, it can be three, depends totally upon the network architecture. And then finally, there is an output layer through which the you know the output is taken. So since there are multiple layers involved, we call this as MLP, multi-layer perceptron process. Okay, so that's another word that you can give to network architecture, neural networking, which is multi-layer perceptron. Okay, so when we talk about hidden layer, we had a discussion on this past as well. The hidden layer is basically a distillation layer which distills or filters some of the important patterns or features from the inputs. Okay, that the process of feature extraction, and then it passes those important features or important patterns to the next layer to observe further. Now this makes the network faster because you are not putting the entire pressure on one single layer, you know. So you are not asking one single layer to extract all the features out of the image. So it is divided between different layers so that they can perform more efficiently. So it makes the network faster and efficient by identifying only the important information from the inputs. So if you are trying to for go for image processing, let's say for example you want to recognize an image with the help of neural networking, then every information or every, let's say you want to recognize a face, okay, face of some personality. Now every feature of the face might not hold that level of importance. Okay, so eyes might be an important part, nose, lips might be an important part, head structure might be an important part, cheeks, I don't think so cheeks play a very important feature in identifying the you know in identifying a person or a personality. So majorly cases, the identification of a personality can be done on the basis of eyes and the nose and the lips area, or the chin area at most. Rest of the things are, or ears, side areas are not very much relevant to image recognition process. So every feature is not important. Every information from the input is not important. So these hidden layers need to distill the important pattern or the important information or the important feature and then pass on to the next layer so that further observations can be done. Then you have the activation layer, which we discussed above as well, that it will capture the non-linear relationship between the inputs. Because if you are not using an activation function, that means ideally you are assuming that there is a linear relationship between two variables. So in more or lesser way, you are actually running a linear regression if you are not using an activation function. Okay, which is not a reality. In practically, you'll find very few examples where a linear relationship exists between two variables. In majority cases, it is the non-linear, which is linear relationship which is in place. So to capture that non-linear relationship, it is important that activation functions are used. Two of the popular activation functions that I have shown you is, one is the sigmoid and the second is the ReLU. Okay. And then there's a final prediction of the output layer. When we talk about the weights, then weights are nothing. They are basically uh, signify the strength or importance of an input signal. So every input signal might not have equal importance for your processing. So some input signals might be given more weight because they are more important. Let's say, for example, the eye structure, while you are trying to recognize an image of a personality, the eye portion might be given more importance rather than the chin area, because with the help of eye area you can eye and forehead area you can recognize an image faster or better. Okay, so every input signal doesn't have equal level of importance, so we need to decide, we need to judge on the importance of that particular input signal and allocate the weight to it accordingly. So weights are nothing. They basically give strength or measure the importance of a particular input signal. Okay, so that's how you can perceive, you can understand the system of uh, neural networking, how it works. Now this is small example. Okay, so I will come to this example later on, This example is again we have taken of how the system of networking works, like uh, how I can predict whether a person will default or not based on certain features. Okay, so in the next session I will discuss this example with you. So now we have actually come on to very significant part of this course, because this is where you need to really concentrate. If you understand how the system works or what are the steps that are involved in a system, trust me, application is very easy. You will not find much difficulties with the code or with the application. It's not difficult at all if you know what are the steps that are involved in this entire process. Okay, so keep practicing, keep learning, and I will meet with you meet in the next session. Thank you so much.